everybody, today we're going to be talking about the phases of the moon and why we see the phases that we see. A few months ago, we spent some time talking about how the moon changes its phase, how it waxes and wanes, where it rises and sets, when it rises and sets, and how it changes its relationship to the sun. Today's focus is why that's going to happen, why we see the phases of the moon the way we do. But before we get started, let's talk about some misconceptions with regards to phases of the moon. Though many people recognize that the moon has phases, a lot of people don't understand why. One of the biggest misconceptions is that the moon has phases because of interactions with the shadow of the Earth. This is true sometimes, but this is only true during rare lunar eclipses. The phases of the moon are not explained by the shadow of the Earth. They're actually explained by something a little bit different, which we'll get into in a minute. The other thing that people sometimes forget is that the moon is visible during the daytime, just as much as it's visible at night. We just sometimes forget to look, and it's outshined literally by the sun, so we don't see that so much. But why the moon has phases is because of an interaction between the part of the moon that's lit up and the part of the moon that we see. As these change, as the moon revolves around the Earth, we see different phases of the moon. So I'll try and explain these to you now. So I know this sounds like a bit of a ridiculous question, but when you look at a basketball or any sphere for that matter, if you think about it for a minute or two, you'll realize that you only see half of that ball. If there were a smiley face on the back of this ball, you wouldn't see it because half of the ball is always obscured from our view. You can see from your perspective out to the diameter, and that's about it. You can't see the half that's beyond that diameter. And this is a really important thing to keep in mind. So there's only half of a ball that you can see. We can also think in terms of this model here, where we have a flashlight lighting up half of a ball. When you shine light on a ball, it only shines on half of it. To show you the same thing here, here I have a globe, here I have a light. When you shine that light on the ball, it only shines on half. And the same thing is true for any light shining on a sphere. It only lights up half. When we put these two things together, so we have the half of a ball that's lit up and we add the observer, we have two halves that we're concerned with. There's the half that's lit up and there's the half that the observer sees. As the observer's perspective with regards to the part that's lit up changes, they see different phases of the ball. In this perspective here, with the person behind the flashlight, the half they see and the half that's lit up are exactly the same. So they would see a full ball, if you will. But if their perspective were different, if they were on the back side of the ball, the part that the observer sees is the part that's not lit up. It's exactly the opposite. So from here, the observer would see none of the ball because the part that's lit up is directly facing away from them. Now we get a little more complicated. If we move the observer off to the side here, we see how the relationship really starts to affect what you see. From here, the observer can see this half of the ball. And they can see that half, and then there's the half that's lit up. So they can see half of the part that's lit up, but the other part is obscured. So they would see a half of a ball, or a quarter of the ball if you want to be technical. But this is, again, part of what they see is in darkness, part of what they see is in light, and so they would see a half of a ball. If we move them back here a little bit, the part that they see includes just the sliver of the lit up section of the ball. Most of what they see is obscured. So they would see a little bit of a crescent of that ball. Not the entirety of the part that's dark, just a little bit of what's light, and so we'd see that. If the observer was over here, again, similarly, they would see most of the part that's lit up and just be seeing a tiny little sliver of darkness, and there's a tiny little space that they can't see. So in this case, what they would see is they would see a gibbous ball, if you will. Right? So the same thing works if we change the position of the ball and the observer. If we move the observer into the center and move the ball around him, we still see the same stuff. From this perspective here, the observer would see the part that's lit up. The part that the observer can see and the part that are lit up are exactly the same. And so this observer would be seeing a full ball, as long as his head doesn't get in the way, but we'll get to that in a minute. If we move the ball around, again in this perspective here, the part that the observer sees shares a little bit of the part that's lit up, and then there's a part that he sees that's dark. So he would again see half of a ball, or technically a quarter of the ball. If we move the ball to here, now we get a little more complicated, but it's still the same concept. For the observer's perspective, he can see only a little sliver of the part that's lit up. So what would he see? Well, he'd see a little crescent. And that's what we'd have if the ball were closer to the flashlight than on the far side of the observer. If we move the ball to the far side of the observer, hopefully you're starting to figure this out. From here, what the observer can see would be a section of the ball that includes a tiny sliver of darkness, but most of the part that's lit up. So from here, he would see a gibbous ball. Well, this is exactly what's going on when the moon goes around the Earth. Of course, there's not a giant head floating in space. That giant head is, of course, the Earth. And the flashlight is the sun. And the sun shines its light on the Earth and on the great big basketball in the sky, our friend the moon. But the perspectives are exactly the same. As the moon goes around the Earth, the part that's lit up and the part that we can see change in relationship to one another. And that results in the phases of the moon. This model that we worked with a few weeks ago shows the same thing. Last time we looked at it, we focused on the top section here. Now I'd like to draw your attention to the bottom. Note that this is a not to scale model, but it's still a really useful tool for what we're talking about. So I'm going to play it while I talk. So here we have the Earth spinning. So we have our day and night going on, and we have the moon revolving around the Earth about once every 28 or so days. On the top section, you can see the moon is slowly waxing away as it goes from a new moon towards a first quarter. Now, as it waxes, you'll notice it's moving farther away from the sun. So the part that's lit up and the part that we see are coming more and more in line with one another. We can see a little bit of a sliver of the moon, so we see a crescent. Most of what we can see from Earth is dark. As the moon gets to this position on the bottom, it becomes, of course, a first quarter. The half that we see and the half that are lit up share a half. So in other words, we see a quarter of the moon or a half of the part that we could potentially see. This entire bottom half of the moon's revolution is when the moon is waxing. It's getting bigger and bigger as it moves from in front of the sun to behind the Earth. And it keeps getting bigger and bigger and bigger. I'm going to go ahead and speed it up and talk once we get to a full moon. And this model is a little forgiving. The full moon is only when it's exactly behind, but here we get the perfect full moon for an instant, but generally the moon is pretty close to full as the part that's lit up and the part that we see are the same. And from here, the moon starts to wane, right? And so the moon starts waning, so we see less and less of the part that's lit up again. Again, it's still a gibbous because it's farther away from the sun, and the part that's lit up and the part we see are still mostly in common. As we keep going, and again, I'll speed it up again. And at this point here, we're about at a third quarter. It's continued to wane, and the half that's lit up and half we see share a half, or in other words, we see a quarter. At this point, we see a waning crescent, and the part that we see continues to have more of the dark part of the moon and less of the lit up part, and so we see the moon continue to wane. And that's it. Those are the phases of the moon, explained relatively well using this model, which is linked from your assignment. Speaking of your assignment, so as you work your way down your assignment and you get to number 14, it's asking you to draw models of the Earth, Moon, and Sun and explain when we would see different phases. If you want, you can just write this out as text, but I think drawing the pictures is really helpful. If you have a computer, I'm going to show you how to do it on your computer. If you want to do it on your phone, come to office hours and I'll explain that process. But it's pretty similar. What you're going to do is you're going to insert shape. And I'm going to insert a circle. And if I hold down the Shift key, it'll be a circle instead of a sphere. And there's my circle I'm going to use to represent the sun. I'll put it all the way over to the left here, and I'll make it a little bit gold. I'll even write sun in the middle of it so we know that that's the sun. Incidentally, I hit a couple of returns after 14 here, so I have plenty of space. If you need to space yours out, you're welcome to do that as well. All right, now I'm going to go ahead and insert the Earth, so yet another sphere. So we'll go Shift and draw out a little sphere here. I'll put a little E in the middle of it so you know that it's the Earth. And then finally, we'll insert one more circle, this time the moon, holding down the Shift key again and making a relatively small moon there. I'll center it. and I'll make it gray because that's a good color for the moon. So there I have the three things in our system. It does say to show the orbit of the moon as a dotted line around the Earth. So I'm going to go ahead and do this too by inserting yet another circle. But this time, again, shift, draw out my circle here. A little off, but pretty close. Now you'll notice, of course, it's filled in and it obscures everything, and that's not what I want. So I'm going to go to Shape Fill and say No Fill. And then it is expected to be a dotted line, so I'm going to go to Shape Outline and go to Dashes and make it a beautiful dashed line. And there we go. Now I have my orbit, and I have my moon, and I have my sun. So I've got all of the model I need. If you want to, I would recommend just selecting all of these items, and then that way you can copy them and paste them to the other questions as well. So I'm going to copy those guys, and I'll scroll down to number 15, and I'll drop them in here, and I'll keep doing that to the other items here. 16, drop them in. A little too low. Let's put them up a little higher. 17 and 18. All right, so now I have those in there for when I need to answer those questions. Back up on number 14, though, the last thing I have to do is the actual answer, which is shading the section where the moon appears as a crescent. So I'm going to insert a shape again for this, and in this case, I'm going to insert a rectangle, and I'll draw it for the section where the moon is a crescent. Now, if I looked at my model from the previous slide here, again, the moon is a crescent when it's on the half closer to the sun, and most of the part that's lit up faces away from the Earth. Here's another model that shows the same thing. Again, we'll see a crescent moon when the moon is somewhere over here. So if I go to third quarter for a second and then play my model, we'll see a crescent moon all the way down this side, barring that little one section where we have a new moon. But for the most part, the moon is a crescent as it's over here. So in my model, I need to shade that section. So I've already selected the rectangle. I'm going to drag that out to about the middle of the Earth. And there we go. Once again, I'm going to make this gray because I think that's a better color. I'm going to get rid of my shape outline here so I don't have an outline around the outside. And I'm going to send this to the back by right-clicking on it and saying Send to Back. That sits it behind the rest of my model, and I've done a good job there. Now I can just copy and paste that and then move it around for the rest of the items that I need to answer. But that's pretty much how you draw those shapes as you answer those questions. When you get to number 18, it's actually asking you about a very specific event called a lunar eclipse. And there's a similar question, number 19, regarding solar eclipses. And these are really neat events that happen with the Earth, moon, and sun. And I want to talk about those for just a second. So remember, the only reason that the Earth and the moon are lit up at all is because of this great big flashlight in the sky, the sun. And as the sun's light is cast on these objects, it also casts shadows. Now, in general, again, and I've said this a couple of times, this model isn't to scale. The Earth is way farther away from the moon. So the shadow of the moon and the shadow of the Earth rarely line up so that they're perfectly on one another. But every once in a while they do. And we get a lunar eclipse when the moon is directly behind the Earth here, and the shadow of the Earth is cast on the moon. So, of course, this has to happen during a full moon, and it's when the guy with the big blue head, his head gets in the way, and we no longer get the light cast on the moon. What do we see when we see this? Well, it's pretty cool. Like we talked about before, the shadow of the Earth goes over the moon, and then the moon turns blood red. As it passes over, we see the shape of the Earth, which we talked about as evidence that the Earth is round. But in its totality, we get this really neat blood red moon. Why do we get that? I'm going to show you a quick video that explains that pretty well. So here we go.
Topic: lunar eclipse. Why does the moon turn red?
Huh? To scare us.
No. Moon does not have a light of its own.
Why? Didn't he pay the electricity bill?
Oh, please listen. Sunlight or white light is a mixture of visible colors. Now, when the sunlight falls on the moon, it reflects all these visible colors equally, making the moon to mostly appear white. However, during a lunar eclipse, when the Earth is exactly between the sun and the moon appears red. This happens because of the Earth's atmosphere. When the sunlight coming from the sun passes through the Earth's atmosphere scatters the colors of the sunlight, having shorter wavelengths. However, red color, which has the longest wavelength, is least scattered. Hence, it makes its way to the moon, making it look red.
And that pretty much explains it. Why we see that blood red moon is because the red wavelengths get through our atmosphere and get to the moon. Pretty cool event. Very much worth seeing next time we have a lunar eclipse here. And as far as solar eclipses go, solar eclipses happen a little bit like the lunar eclipse. We see a shadow cast on another object, but the difference here is this time it's the shadow of the moon cast on the earth. So we see that shadow pass in front of the sun, and then the sun gets completely obscured, revealing nothing but this beautiful corona or the bright light around the outside edge of the sun, which we normally don't see. Really neat event. I've never actually seen one. I've seen a partial solar eclipse, and that in and of itself is pretty darn cool. But that's it. That's pretty much explains everything on your worksheet, why we have eclipses, why we see lunar phases the way that we do. If you have questions, feel free to ask.